Good evening, ladies and gentlemen and structural engineers. Welcome to an evening of introspection and discussion of building safety. The unfortunate incident of the collapse of the Champlain Towers in Florida State in USA has prompted us to convene today to look back, to go ahead. The program today is to listen to some reflections of four persons in structural engineering, two of whom practice structural engineering towards building the nation, and two of whom prepare the next generation to practice structural engineering towards building the nation a little ahead in time. The first hour will be spent on listening to their thoughts, and the second on listening to your thoughts and questions. I hope you will find this evening well spent, and without further ado, I invite Ms. Alpa Sheth, Managing Director, VMS Consultants Private Limited, Mumbai, to share her early observations on the collapse of the Champlain Towers and point to implications for building safety in India. Ladies and gentlemen, please welcome Ms. Alpa Sheth.
Thank you very much, Professor Murty. Good evening. It's good to have all of you out here. And I think today is going to be a day when, while we mourn what has happened, I think we also need to understand that the collapse of this east wing of the Champlain Towers South has turned the spotlight on safety and stability of structures in general, and that of flat slabs in particular. I think this has been undoubtedly one of the biggest building collapses and disasters in the last few decades to happen in normal times. That is without the trigger of a natural disaster such as an earthquake or a terrorist attack. The formal investigation is underway. I believe NIST is doing it. We will, in the course of this evening, use this unfortunate event as a backdrop to review the way we design. Is underway. I believe NIST is doing it. To review, we will, in the course of this evening. I'm afraid somebody's. I'm getting an echo. To review the way. Okay, thanks. We will, I'll just repeat myself a little bit. We will, in the course of the evening, use the unfortunate event as a backdrop to review the way that we design and we build. We will also visit some of the unrecognized vulnerabilities that are inherent in some of our building systems. My presentation will focus on the event and the preliminary observations based on gleaning gigabytes of information available from the official and other sources, along with some initial calculations. So let's start right away. Just so that we have some idea of what happened, I would just like to take you through really what was in real time at that time, what happened. And what you can see is the central part collapsed, and then the easternmost part of it collapsed. Right? Okay, so I think we need to keep this sequence of collapse in mind as we go further. Okay. So I think what was the good thing which we have learned from this is how cities react and respond to such a disaster. So the town of Surfside, which is just off of Miami, Florida, within a few days of this collapse, the town uploaded all the data which it had accessed and which it had in its storage. It was uploaded on their website. And there are some documents of what were the survey reports. But more importantly, there are 300 drawings and construction documents, which include, of course, numerous repeats and revision updates. But together, it is possible to piece a large part of the puzzle, so to say. And I think this has really helped all of us across the world to sort of understand what could be the possibilities of of how such collapses can happen and what are the vulnerabilities. I also hope that our authorities in India will take a leaf out of this, and data is shared after any major failure in the future, so that the culture of learning from failures is institutionalized, right? As you can see from the structural information, the building was about 250,000 square feet, which is no small area. And it had 13 suspended slabs, which was one basement roof and 11 floors and a roof. And what would be really interesting for us is that which is not permissible in India as of date, at least, that the typical floor height was 2.64 meters, which roughly works out to 8 feet and 10 inches. And I think what would be interesting for structural engineers over here would be that the entire project data for construction and the entire set of construction structural drawings were squeezed into 14 structural drawings. And I would say that, you know, while we may all marvel how somebody could actually have realize such a feat, I think we should remember that this was a time of manual drafting, and there was a tendency to be economical in the production of drawings. And it's very different from now when we have one base drawing. It's so easy to produce 50 typical drawings of different floors and so on. So now let us just understand as to what happened. If you recollect the sequence of failure that we saw, you will remember that the yellow portion in the slide, which is in front of you, that was the first to collapse. The little strip at the back was the second. And the first and the second collapsed immediately, one after the other. And then there was a bit of a pause. And then the lavender colored part was the one which collapsed subsequently. And I think what we would do is to understand what happened and why, and the green portion, it did not collapse, and what was the point of a separation between the collapsed and the part which is still standing, which is the western side of Champlain Tower South. As you can see, the collapse progression was stopped by this long shear wall, the reinforced concrete shear wall. It was about 56 feet long and about 1 foot or 300 mil thick. And pretty much what you see is that the portion to the west of that wall has survived, and that to the east of it has collapsed. And there are about 136 units in this tower. And you can, I think, have a glimpse of, you know, this is an architectural drawing on which we have overlaid the sequence of collapse. And out of 136 units, 55 of them have pancaked. And as we speak, there are still 121 people missing. And as the days go, I think hope also recedes, unfortunately. Now, you know, I just want you to focus your attention on this wall. Okay, so now if you look at this wall, this is the wall that we are talking about over here. Okay, so this wall, the collapse in this lower portion, which is where the eastern wing of Champlain Tower South was, as you can see, a pancaking kind of behavior, and it's pretty much just, you know, it's just really like the different slabs have just kind of pancaked one on top of the other in a vertical manner. So I think it's important to also park that thought that it looks like a vertical collapse of the structure. And I think also what you may want to see is the wall, which we said was like a rampart, right? Which stopped the march of the collapse. This particular wall, which is, as I said, 56 feet long, I think it would interest all of you. When I first saw it, and it was a reinforced concrete wall, and yet I said, my God, it looks as smooth as a masonry wall. There's hardly any kind of reinforcement or doubles that we are seeing, because this was the portion where it was engaged with the flat slab. And maybe that is also something which is a revelation, and we will explore that a little bit later in this presentation. Now I'm going to go through all the 14 drawings. I think a large portion of our viewers today are structural engineers, and at the risk of, and I'm not going to be very technical, because I do know that there are some architects and other interested people. So while we will be technical, I'll try to keep it simple. So I'm going to take you through all the 14 drawings that were there, and I think that that may give some indication of how and what they had done. And I think I'm just going to walk you through the same exercise that I have done in the making of this presentation. So basically, first of all, this area of Miami is reclaimed, and this particular building was on pile foundations. I believe a lot of the reclaimed projects, a lot of projects on the reclaimed land over there are on pile foundations. And there are, as you can see in this picture, you can see square pile caps and triangular pile caps. And this is a slightly dated picture. I could not find the most updated picture, because there are some hexagonal pile caps here, which actually were not really built over there. But what I would like to draw your attention is to these two pile caps, which are eye-shaped, one here and this large other pile cap, which is for the 56-foot wall. The other point of note is that there are no tie beams. Now, Miami is, as we all know, subjected to a lot of cyclones, hurricanes, gusty winds, and so on. But to the best of my understanding, it's not a high seismic zone. But it's just a point I'd like to park with you, that there are no tie beams over here. So it's one more situation that you get several opportunities to provide some kind of redundancy, and sometimes that opportunity we sometimes don't exploit it for various reasons of economy and also client pressures and so on. So what I would like to say is, I sometimes when I was looking at it, I marveled at some of the thinking which has gone into the project, because if you see all these eye-shaped, the long shear walls. The consulting engineer, the structural engineer, was aware that these are going to be the primary lateral load resisting elements. And therefore, if you look at the piles, that's why it has the two flanges. This pile cap has two flanges, and those flanges of the pile cap have tension piles. So all of these piles which you're seeing in the four flanges on this drawing are all tension piles. But at the same time, it's also an enigma that while there was due recognition of the fact that you needed to have a lateral load resisting system in the north-south direction, there was practically no lateral load resisting element in the east-west direction. You just have these two piddly walls over here. And so I'm not sure that I don't want to distract, and because we are not really talking about a lateral load kind of situation where this collapse has happened, but I'm just in general, when we are talking about issues of structural integrity and robustness, I think it's important to talk about these issues, because sometimes when you give a lot of integrity and robustness, it also helps in civilian or in non-lateral load times. Like, for example, we saw that this particular shear wall was working as the fortress, as the rampart for stopping the collapse to go further onto the western wing. Now, looking at what were the typical building dimensions, see, these were modest spans as compared to today's times. And just to tell you, the last drawing I saw was dated early 1980, but most of the drawings are dated 1979. So I believe this project must have been constructed in 1980. So as you can see, the flat slab spans are pretty modest by today's standards. You know, it's just about 7 meters by 6.5 meters. You know, it's not something we would worry very much in today's times. And the basement roof was, of course, practically the entire complex area, the footprint of the plot was covered by the basement. And so you can see this whole region which had a suspended slab, and the 3 parts which collapsed, and the green which was standing. I haven't yet shown what happened, because this was the basement roof. On top of that, there was another podium slab, which we will talk about. This was the lobby level floor plate, and this also extended to the full area of the plot, practically the full area, you know, save a marginal space on the edges. Now, if you had a look at the photographs in various media, and we'll show you some more over here, the area which is outlined in red was the slab at the lobby level, or the first floor as we would call it. That entire slab of the first floor had given way. Only a certain portion around the swimming pool stays, but the rest of it has given way, except of course for the western wing of this tower. And as I had said, the basement roof was 240 mil thick. The lobby level, or the first floor, was 9 inches thick. Now, I just want to again draw your attention to one point. This little blue circle which I've marked over here. Now, there's a column here. It's, of course, I'm not sure you can see it, but you can just believe me when I say that there's a column over here. And this column is the column which goes all the way to the roof level from the first floor. It's going to 11th floor and then roof, and that is sitting on a floating column. Let me rephrase it. That is a floating column which is sitting on a transfer girder. That is not the cause of anything, but I thought I would just point out to you. But there's something more interesting which comes subsequently. And one thing which is interesting is, if you see this blue rectangle, as you can see, there are columns on that red line, which actually are the tower columns for the green area, which is still standing. And they also are the columns which engage the podium flat slab, right? Which has collapsed, okay, which has collapsed. But these columns are still standing. So these are the columns I was talking about, which I had marked in the previous slide. Now, I just want to draw your attention to these 2 yellow ellipses which I have drawn. And you can see there's hardly any sign left of any slab having been here. It's almost like a cake cut, right? And while you can say it was punching, you can also say it was a slipping of the slab. But one thing for sure you could say is that there was very little anchorage of the bars of the slab going into the column. What you can also see, interestingly, on the right side are these columns, which are 3 to 4 stories long. Okay, so these are columns from the tower which have fallen down, and they have continued. What you can see over here, if you can see my cursor, is you can see and you can locate where are the pinching points, are the points where the slab was. So again, over here, what you're seeing is a complete disengagement of the slab, and very likely these should have been perimeter columns, which disengaged from the slabs, and of course they have fallen as one continuous element. And over here, if I have to take you back to this tower and these columns which are still standing, if you look at the drawings which are available, what the drawings indicate to us, as per the drawings, there had to be 4 number 5 bars. I mean, those of you, just to set this, when I say number 5 bars, it means that it is a 16 diameter bar. Okay, number 8 bar is a 1 inch dia bar or a 25 mil bar. And number 5 is 5/8" dia bar. So that is a 16 dia bar. I've just kind of picked it up from there. So now we should have seen 4 numbers of 16 dia bars on each of the faces of the column. Each of the faces of the column should have been showing us 4 numbers of 16 dia bars, which were at the top, slab top reinforcement. And we should have seen 16 dia bars. We should have seen 16 dia bars at the bottom, which should have been at least at, we should have seen at least 2 bars. We should have seen at least 2 bottom bars, and we should have seen 4 top bars. But as you can see, you know, in this column, which is to the right, there it's again, it's so clean. So there's one thing which we can see is that there was an anchorage problem in, and the engagement of the slabs with the columns seems to have been problematic. I just wanted to show you some more of these long columns which you're seeing, which are double story, triple story, and they're all over. You can see them everywhere. So you know, so in a way, the failure, the understanding of punching failure and so on would be something which will be a matter of great discussion in the months and years to come. I'm now going to take you to the second floor. We've gone through the lobby level, and that was the first floor. And this is the drawing number 6 out of the 14 drawings, which is the second floor plan. Now, here's where the fun begins. The entire area which is green, I mean, the entire area except the top 2 bays over here, the entire area, all these columns, if you look at the box which has been blown up, all these columns which are supporting the 9 slabs above, or sorry, the 10 slabs above, all those columns are floating columns which have been floated from girders which are on the second floor. Okay, what is interesting is the east wing, which is collapsed. It had 1 column which was a floating column, but the west wing, which is standing, has all of the columns, I mean, except for the upper 2 bays, the upper 2 bays, meaning the northern 2 bays, except for those set of, but you know, I don't, again, let's not get distracted, but I just thought it's a fun fact to kind of, you know, note. And so you have these floating columns which are taking 10 stories of load. 13 suspended slabs is the second floor, so 10 stories of load, which is on these columns, and there are these transfer girders which are transferring this load from these columns onto that. And what is interesting to me is the kind of transfer details. Remember that this project has been completed in 14 drawings. So there's a certain efficiency which has been kind of applied to the production of these drawings. So this, I've just blown up that particular one set of transfer girders, and you can see that this is the column which is stopping, and all these which are shaded are the columns which are going up. So you're seeing this one column which is over here, and the other has just, it's not a large, but you'll have very high shear forces, of course. But I just thought it would be interesting to see the kind of detail. So there's just one typical detail. All of these beams which you're seeing, all of them, with the exception of 2 beams, all of these beams are transfer girders, because as I said, you know, all of the columns have, I mean, pretty much all of the columns in the west wing are floating. So there are lots of transfer girders. So this is the beam schedule for those transfer girders. This is the typical detail, and I just have circled what I consider as very interesting detailing. And I'm not sure about the development and you know, of the bars. And also, if you look at the circle at the center at the bottom, there is no bars go continuously in the bottom. So there's obviously no fear of any reversal of stresses. But you know, these bars are not just for reversal of stresses; they are required for integrity of the structure, for robustness. So this is a pattern which also is something which you're seeing not only in these beams, but you're also seeing it in the slab detailing. So we will go further on that. So, but of course, again, I repeat that these are transfer girders, but that area is just standing. I've already talked about it. So this is the portion of the floating. So this is the floating column area of the building, if I may. Now I'm just going to show you this typical floor. Basically, I know that the drawing is too small for you to see, but let me just kind of share with you the information on it. It is 8 inches thick, 200 ml thick. It's a flat plate. There are no drop panels. There are no column capitals. But as I said, the spans are quite small, 21 feet, 22 feet, and so on, 6.5 meters, 6.9 meters. And there is a continuous bottom mesh, which is number 4 bars. As I said, number 4 would be 12 mil at 325 center to center. I mean, I guess, because I've converted it from inches into millimeters, you could consider that it was number 12 at 300 center to center. And then at the supports, that is the cord, sorry. At the column strip, there are 16 numbers of 16 dia bars. So that works out to 16 dia 200 center to center. And in the middle strip at the support, you have 12 dia at 300. So here in this long wall which we were discussing, what we should have seen is 12 dia at 250 center to center along the full length of the wall, because that's what the detailing is. So let's blow up this wall and let's see what really happened over there. So this is, as you can see, I'm just seeing it over here. This is the view, and I have blown up this wall, which is on the left-hand side here. And look, on these 2 floors, I just don't see any reinforcement here. On the uppermost floor, there is a little bit of reinforcement. Maybe it is at 300, but what is very interesting is suddenly just look at this whole bunch of reinforcement, and I'm not plussed, because at least in the drawings which I have been able to access from the whatever 336 drawings or whatever, I could not see this reinforcement called out in any drawing. So I think that this particular project also has some challenges in terms of the construction and how it was done. And I think that's something which will be studied in great detail by the investigators. Okay. This is a penthouse drawing. It's very similar to the typical. I'm not going to spend time on it. Again, in the roof level, the only reason I thought I'll just spend a minute on it is, again, this problem of detailing. All of us would have expected that when you have some such system, you would be expecting a kind of portal action, right? Anytime you have this. And it's very interesting detailing, because I guess, all of us had learned to do detailing differently. But see, as everybody says, oh, but the building stood for 40 years. And it has stood for 40 years. And these are not the reasons why the building has collapsed. But, these are very interesting details, if I may. I think that's one thing which we learned in college, that just because a building stands for 40 years does not mean it was safe. It just means you were lucky, right? And now let me share with you the drawing number 11 of the 14 drawings. This gives the details of the slabs. Now, this is the column strip that you are looking at here. And this is exactly what I was saying, that first of all, only 50% of the bottom bars have been continued, and that's okay. That's what even our codes allow us. But then there is only a 6-inch overlap. Now, this is very problematic in terms of integrity. Unfortunately, as of date, our Indian code, IS 456, does not address this issue of integrity steel. But I think this is something which is there in a lot of codes. It is there in the Euro code. It's there in the Canadian code. It's, of course, there in ACI. And I think Hemal may be talking perhaps a little bit about that. So I just kind of felt that, there are some problem points, but then you have a situation, and each of these challenges by itself may not have been so bad, but then you have the cumulative effect of a lot of issues, and that can sometimes, at some time, in some stage of the life of a building, cause immeasurable damage and loss of lives. And so basically, as we said, that if you do not have integrity, I'm not implying that if you have integrity, still the building is going to hold. There is no, the building is still going to collapse. I think the question about, you know, flat slab buildings is we have to accept that by its very nature, it has limited or almost no redundancy. And so we have to then think about, if it fails, it's very likely that a collapse may follow. So then the challenge for a designer is, how do I ensure that even in its collapse, it is going to allow for safe egress of all of the inhabitants of the building? I think that's the challenge all of us and all the codes are grappling with. And this, as we saw just in the beginning, that in less than 15 seconds, this building, which must have been, you know, say it was about less than 50% of the building. So I would say at least about 150,000 square feet. I'm sorry, yeah, about 110,000 square feet of the building just collapsed in less than 15 seconds, right? So that's something which is something which we need to mull about. I'm going to show you this drawing, which is just a simple drawing for the walls. As you can, I'm not going to comment on any of the detailing or anything, because it's out there for you to see it. And if you cannot see it over here, it's available on the website of the town of Surfside, and anybody can access it. As I said, there are some 336 drawings, but only these 14 drawings are of use to you. I think the challenge is just to pick the right ones. I've already talked about the fact that, you know, you don't have any walls east-west, and the reinforcement was, the thickness was good. It was 300 mil, and it was, the spacing was 12 at 300. Of course, as I said, that this is not a seismic area. And again, we're talking about a building which must have used ACI 77. And even in the US at that time, there was not so much of a development of confinement requirements for boundary elements and so on. So we will not see that, and we should not expect to see it. Having said that, I think that there was a realization that the long walls are going into tension at the edges, and that has been addressed. That has been addressed in the long wall, which is 56 feet. Okay, one always leaves the fun part to the not fun part, the tragic part, but the most eye-opening part to the last. And we come to the columns. Okay, so what were the column sizes? I left it to the last. The columns are the same size from the pile cap to the roof. Okay, that's fine, because, you know, I mean, I guess for ease of construction and whatever. So the columns in the east wing, which collapsed, they were actually carrying 13 suspended slabs, right? And they were sized 350 mil by 450 mil, which is 15 inches by 18 inches, right? On the other hand, the columns on the typical floor on the west wing, right, which these columns, remember, were starting only at the second floor, right? So they were only carrying 10 slabs as versus 13 slabs of the columns on the east wing, right? So these columns of the west wing are 12 inches by 24 inches or 300 by 600. So now if you calculate that lesser number of floor loads to carry, a lesser number of floors to carry, and having a size which is larger, you will find that the stress ratio, the stress which would be there, or the stress comparison, if you make, you will find that the west wing columns had only 67% of the stress as compared to the east wing. And that is one very important story. Yes, it is the shear wall which was very good, but, you know, I mean, it's not a fortress. So there was another reason why that side actually survived, despite having had quite a bit of unbalanced moments, you know, the effect of the deformations on the other side, because it was one building. But it had 33% lesser stresses than the east wing. So that's something to note. The concrete grade, which is interesting for us, even in the 80s in the US, the equivalent cube strength, the FCK was M50 and so on, M50, M45, M35, and so on. Now, if I were to talk about, I'm sorry, I'm almost, I should be finishing. Excuse me, apologies. I've taken a little more time than I should have. So I'm just going to, but because this is most interesting part of it, I think you must bear with me. The preliminary, I'm going to show just the calculations for this one column. Okay, I just picked one column from the east wing towards the front, but it's not the perimeter column. It's the penultimate column. Now, I did two calculations. One is as per IS 456 and SP 16. I converted the concrete to equivalent cube strength and so on and so forth. It's Fe 415 steel. So for the estimated service load, okay, so basically I'm doing working stress and I'm not taking the full design load. I'm just saying, you know, because in design load you may take 2 kilonewton per meter square of live load, and I'm saying, you know what, there wasn't 200 kg per square meter or 2 kilonewtons. So I've taken just about 0.6 kilonewton per meter square and so on and so forth. So I have calculated that what would have been the estimated service load at the time when it collapsed. And I'm getting a PU or FCK BD is working out to be 0.58. And if I had to do a limit of that, you're coming to 0.78. But when the building was designed, of course, it had to be designed for the design service loads, which would have been 0.62. And then the limit actual stress ratio would have been 0.85. Okay, so that tells you a little bit of the story, right? Again, added to that, you have reinforcement corrosion. Now, with this kind of, so the other important thing to understand is that these columns were small, but they had huge amount of steel. They had huge amount of steel. The steel was 10 numbers of 36 dia. 10 numbers of 36 dia, which works out to 5.9%. Okay, I don't know how they were able to do the splicing of the bars, because at that time, I think you were even allowed to do all the splicing at one place. So how would you manage 12% of steel? So that's something which I don't understand. Maybe that also gives us a clue to what may have happened. I don't know. But I would just like to say that with these kinds of stress ratios, I think it's a no-brainer. You would know that, you know, with even just a 5%, just you know, just for pure action loads and nothing else, you would require 4.2% steel, right? That's what's the most. But you, in a flat slab, you are going to have a certain amount of unbalanced moments you have to design for. And if you just take a 10% eccentricity line, you would have required 6.4%. That is also for the estimated service loads. And then if you take the design loads, then the reinforcement you would have required is 7.8%. What is provided 6%. But let me show you now as per the ACI code. I'm not going to get into it because I've already overshot the time. But if you look at what is the ultimate capacity based on the ACI code, I would get 517 tons. And what is the ultimate demand? It is 671 tons. So the demand to capacity ratio is 1.3. Let us compare the ultimate capacity to the service demand. Okay, but even then, if you look at that, we are saying the capacity is 517 tons and the present service demand as of the day it collapsed was 498. Of course, you know, these are all, you know, very estimated. These can be off by 10%. So you can see that the service load, not even the ultimate load, the service load also was just about what was the ultimate capacity. So if you look at this picture and you look at this circle, which is marked, this is where we were. So there was practically zero flexural capacity. And you know, I think Professor Goswami is also going to talk a little about this. So I will leave it there. I checked the punching shear. The punching shear is not a problem in terms of the capacity of the slab. The demand to capacity ratio was coming out in the range of 0.75. And so punching shear by itself, the slab would not have perhaps given way unless there was a loss of a support, right? So you know, it's something to think about. And the punching shear was observed on the podium slab and in tower slabs. And of course, corrosion also can play a part in the reduction of punching shear capacity. You know, the punching shear or the slip of the of the slabs was also happening because of the lack of anchorage, right, between the wall and the slab. So if I have to show you the punching shear which was there on the podium, you can see all of these columns standing there, and you can go down to the base of it and you can see the punched slab over there, right? So this is the punching which you're seeing in the podium slab outside the tower. And then if you look at this picture, and you look at it carefully, you'll see some of these columns, which are the tower columns, which are also exhibiting punching shear. You know, you can go down to the base and have a look at it. These are all pictures on the web. Just take some time out and zoom it, and you'll be able to see it. So if so this is really all. I've taken it through all the 14 drawings and what we could glean from the information available there, also doing some of the calculations which are not really a very detailed analysis. But there were a host of stories which emerged just from very basic calculations. And just in closing, I would like to say that, you know, we all know that it suffered a brittle, sudden and cascading failure. And whatever is the information we have been able to access and whatever are our preliminary calculations, they seem to suggest that this vertical downward collapse may have been triggered by a column failure. Because as I walked you through it, the design of the columns was marginal. And of course, there is very little redundancy in the structure, in this type of structure. And it's compounded by the fact that all the anchorages at all the junctions, at the connections, was rather poor. And there was no requirement of integrity steel in the flat slab. So therefore, even there was no possibility for the flat slab to fail gracefully and give some amount of time for a possible egress, even for 10% of the people or 20% of the people if there was time. But 15 seconds, nobody can do it. It was less than 15 seconds, actually. It was 12 seconds. And as I said, the reinforcement of the slabs was not placed as per the drawings. As we saw, it was missing at locations, and at some places it was just bunched up at a place. We don't know how that happened. And the punching shear situation was observed in the podium slab and in the collapse slab, but its reasons are not, I mean, that may have been a secondary collapse, right, triggered by a primary collapse. Okay, that's all, folks. Thank you very much. Sorry, I'm going to pass on the screen and the mic to Dr. Goswami. Professor Rupen Goswami is going to take us through more in-depth understanding of failures and behavior.
Thank you. The calm before a storm is very important, a moment, because it gives an opportunity to look at the past and prepare for the future. So after such an eye-opening presentation, I'm sure you all are eager to get into, doing more dissection, more discussion on analysis, design. But before you get on to those, I want to draw your attention to a very fundamental thing in structural engineering, that is to have focus on structural behavior. While the sophistication of analysis and details of design are important, if we lose focus on structural behavior, none of that will help us in the long run. So today, I'm not going to discuss collapse of any one building. Very good evening, ladies and gentlemen. My name is Rupen Goswami, and I thank you all for joining us today for this special occasion. And in particular, I thank SEFI for giving us all this platform to be together. Collapse is a very important issue in structural engineering. And collapse doesn't happen just like that. There are multiple stages through which a structure has to pass through, go through, for it to collapse. And to begin with, I want to set those ideas straight. When we design a structure, it is subjected to either some forces or displacements, and accordingly they respond, and we expect elastic behavior out of our structures. And that is what most of the time should happen in structures. But then sometimes there will be damages, and this is where it all begins. And I want to emphasize that damage is not collapse. There are good damages, there are bad damages, there are certain locations where we can afford to have damages, but that need not cause collapse of a structure. Because if we allow for redistribution of forces in a structure, simple damages will not lead to, should not lead to collapse. Going further, there can be failure, and failure is again not collapse. There can be failure of an element of one component, which is a local failure. And again, if we allow for redistribution, I'm sure you'll agree, a structure should not collapse. So what is collapse? Collapse happens when we allow a damage to progress to a collapse or to a failure level, and then we do not contain that and do not allow redistribution of forces to happen within the structure. That is where we see a global collapse. So it's a long process, and it's not easy for structures to collapse. That's the first idea I thought we should all have in our mind. So when we see a structure which has collapsed, we need to understand that there must have been some basic fundamentals which were missed so as to cause this. So how does this whole thing happen? As I said, damage can be good damage or bad damage. Essentially, I'm talking about ductile versus brittle actions. So when there is a force loading, if we do not allow redistribution, of course, that gap between the initiation of the damage to final collapse can be very fast. And that is where we always think of having a more prolonged plastic deformation capacity to be available in structures. Now, when you see this drawing, don't think that I'm talking about lateral load, lateral displacement relation. This is true even for vertical deflection analysis under simple gravity loads. And that is where we are all taught the difference between over-reinforced and under-reinforced sections, shear versus flexure, and so on and so forth. So I'll continue to use this load deformation graph, which can be for both vertical as well as lateral actions. Talking about good structures, they need to have at least 7 key virtues. But the first 3 quantifiable, most important virtues are stiffness, strength, and deformability of a structure. Let us look at each one of these one by one. When I talk about stiffness, we need to first talk about vertical stiffness. It can be due to the soil. So the first item is the soil. We know there's a long-term, short-term deflection, deformation, consolidation, and so on and so forth. But what is important is to understand if there is a possibility of differential settlement due to soil and due to foundations. And that is where some of the simple structural elements do help structures. Because if our design is going to be almost to the limit, then we may not have enough margin to accommodate the simple actions that may arise. The next most important thing is vertical linkers, and needless to say, in most buildings that we design, these are our columns. Today we have a situation where we want to move to high grade of materials, high grade concrete, high grade steel, and the first motivation for going for these is to reduce sizes of vertical elements. What does it lead to? Small sizes will lead to low axial stiffness, and there will be axial shortening of members. And if we, do not again account for this, simple unequal axial shortening will induce additional stresses in our systems. That's the first thing. The second thing, of course, small sizes will lead to very high axial stress ratio. And we just saw the level of axial stress ratio that were there in this particular case. So this differential settlement or shortening and high axial stress ratio are definitely not good for our vertical members, and we'll see that. And one important thing to remember, which is beyond our regular design calculation, is that when we have high axial stress ratio, it kind of helps in accelerating corrosion. And so effectively what we have is, we have reduced margin of safety in our system than what we have considered at our design stage. So how do we address this? Is it time to think of a certain minimum structural plan density, not from lateral load resistance point of view, but simply gravity load resistance carrying point of view? We need to think in this line, is what I believe. Moving on to lateral actions, again, the first issue is soil flexibility, foundation flexibility, as always, and in pile foundations and things like that, the depth of inlet. We often do not take into consideration some of these items so precisely, and these do affect lateral stiffness of a structure. This is where I want to bring in the issue of having wall in a system. So what we see is, if we have walls offer significant amount of lateral stiffness to our buildings, which effectively helps reducing displacement. Moment frames are good, but they are much more flexible compared to wall frame systems, and so lateral deformations, even due to simple eccentricities and normal lateral loads, will be much more in moment frames compared to wall frame systems. But what is a moment frame? Moment frame is when we have a horizontal member and vertical member acting together. And just as two extreme examples, we are seeing a situation where we have a column and a beam, and the beam on the left side is stiff enough. That means it has sufficient size and stiffness. Whereas on the other side, we have a very flexible beam, or sometimes no beam. I mean, in which type of systems you have such beams which are missing. So what does it lead to? If we look at the vertical members, the stiffness of the horizontal member, the beam, critically affects the bending moment, the actions that develop in the vertical members. So while we consider our columns to be bending in double curvature, what happens is, in the absence of beams or adequately stiff horizontal elements, these columns are subjected to significant amount of bending actions, additional flexural actions, which often we might not consider in our design. This next issue is about connections. So we have the horizontal member and the vertical member. What about the connection? We might have good horizontal member, but if the connection is flexible enough, or in situations where the connections fail, again, the same situation happens. The columns go in single curvature bending, and significant amount of additional moment gets generated, in addition to, remember, the high axial stress ratio that it is already carrying. So now you can imagine what is the expected fate of these columns. So effectively, if you see a system which doesn't have good horizontal element, or where there is a chance of failure of the connection between the horizontal element and the columns, you can safely say that those structures have no lateral load resisting system. Because once there is a failure in the connection, there is no scope for any redistribution in those structures. Moving on to the next item, which is strength. Now, I started off with damage, and damage is always related to strength. We know that there are good damages, ductile damages, and bad damages, brittle damages. So we say that we need to allow damages to happen in certain good places in a structure. And usually those are the beams. But if you do not have beams, then what you are left with is only allowing damage in all the bad locations, bad choices of locations that you have. You do not want damage in your joint, in your connection. You do not want damage in your vertical elements. But that is what we'll be left with if we do not have these beams. And needless to say that any type of damage in these members are not going to be ductile, but very brittle. And so the gap between the initiation of the damage to final total progressive collapse is going to be very short. Let's look at this PM interaction diagram a little more closely. All of you can recognize that these are, this diagram is from our SP16. We all have used it, and it is in existence for decades now. I would like to draw your attention to these radial lines in particular. So you see, I have highlighted one particular radial line towards the bottom of the diagram in green, and another one in orange at the top. When we provide reinforcement, we want the reinforcement to go in tension, because that is what gives us the possibility of allowing yielding of the reinforcement and giving us a ductile kind of an action. If you cross over the orange one, that line in SP16 is written as FYD is equal to 0. That means there is no tensile stress in the reinforcement. The entire cross section is in compression, and so failure is going to be governed by sudden crushing of concrete alone. Steel is not going to help. So no matter how much reinforcement we provide, the failure is always going to be brittle in nature. Let's look at the PM interaction with a little more detail added to it. We have always seen the diagram, but another important thing to note is that at each of these axial load levels, if you draw the moment curvature or moment rotation, whichever way you want to put it, this is moment curvature, you will see that below the balanced point and up to the balance point, the failure is ductile. That means the reinforcement that is provided actually is acting and making it ductile enough. But when we go for very small size columns with high axial stress ratios, three things happen. You're already very high up here, and by this we know that the failure is only going to be very brittle in nature, and you have very little margin, and it doesn't have enough margin to accommodate additional moment that may get generated due to various accidental reasons or lateral loads coming on it. So the only way these kind of systems will fail is in a very, very dangerous brittle mode. That is why in some codes, at least they say that we need to have a limit on the PM interaction diagram below which we should design our columns for. If we cross that limit, we will be getting into dangerous territory. And I think that is something that we need to critically look at. The third item, of course, is deformability. And note, I'm not yet spoken about ductility, because collapse is that deformation after which the system is rendered unable to carry even the self weight, right? When somebody faints, we say person collapsed. because it's not able to stand, not able to carry the weight of the structure itself. So in this whole process, until collapse, there will be damages. And we want the redistributions to happen so that many more locations participate in this whole process until the final collapse happens. And that will be possible only and only if we provide for redundancy in the system. If there is no redundancy in the system, collapse will be very sudden and brittle. And finally, of course, when we try to talk about having an enlarged plateau length of plastic actions, one important thing that we need to always remember is that the first location of first damage should continue to have the plastic rotation until the collapse point. If the first point fails, the collapse happens when the first point reaches its deformation capacity or deformability. So if we want our structures not to collapse by providing with adequate deformability, the location of first damage has to have that plastic deformation capacity. If we do not ensure that, structures are likely to collapse. So if I look at it, really speaking, structures should not collapse. All the good things that we were taught in our colleges had many elements in them that would usually not allow structures to collapse. But when we start putting all eggs in one basket, we put ourselves and our structures at risk. When you have a system like this without any load path, other than allowing or making all the forces to run towards one point in the structure to get transferred to move downwards to the foundation, we are inviting trouble. And as progressively as you come down these columns, vertical members, if their axial stress ratio is not controlled, then of course we are likely to see brittle failure. So in summary, I'll say that while we pay a lot of attention towards lateral load resisting system, what appears to be very important and coming out through this exercise is that we need to care about gravity load carrying elements first, because gravity loads are going to be there 24/7, 365 days a year. We cannot miss out on the gravity load carrying elements. They need to be stiff, they need to be strong. We need to ensure this. Then, of course, we need to ensure that there is adequately stiff, strong, and ductile lateral load resisting system, because there can be accidental eccentricities and lateral loads coming on the structure, even if we do not envisage such things at our design stages. And finally, redundancy is very, very important in our structural design. So I guess we have a lot to think about before finalizing or kind of saying that what exactly we need to do in terms of our design. Okay, I'll stop here for now. Thank you for your attention. Let's build a safe India. Thank you. So now I request Sri Hemal Mistry ji to come forward and make his presentation on some of the very critical details of design of these systems that he has made a presentation. Please come.
Thank you, Rupen sir. I am Hemal Mistry. Today I am going to discuss about design of flat slab and various codal provisions in international standards and in Indian codes. I will focus on punching shear design and on detailing of integrity and redundancy reinforcement. For punching shear stress, the requirement in IS 456 and in ACI 318 are similar. The critical sections are at D/2 from face of supports. The shear stress shall be calculated by combining shear stress due to unbalanced moment with the normal shear stress. Only one moment shall be considered at a time. Now, this calculated shear stress shall be compared with the capacity. Now, the punching shear strength of concrete, which triggers the requirement of shear reinforcement, can be calculated as 0.25 square root of FCK into 0.5 plus BC. That factor BC takes into account the effect of aspect ratio of column. In ACI, three equations are proposed, and that takes into account the effect of depth of slab, the shape of column, or say aspect ratio of column, location of column, so whether it is interior column, edge column, or corner column. Generally, we do not have edge or corner column as 1893 requires a stiff perimeter beam. Also, it takes into account the effect of critical perimeter, size of critical perimeter. Recently, the depth factor lambda s is introduced in ACI 318-19. And as the depth of section increases, the shear capacity of concrete reduces according to this factor. Now, once the shear reinforcement is required, the shear strength of concrete shall be specified. The requirement is more or less similar in both the codes, except the depth factor is introduced. This depth factor can be neglected if some minimum shear reinforcement is available. Also, the equation specified is applicable when the stirrups is used as punching shear reinforcement. Some more shear capacity is allowed when stud shear reinforcement is used. The maximum punching shear stress, which governs the thickness of slab or say size of column, is also similar in both the codes when stirrups are used as punching shear reinforcement. Larger capacity is allowed when shear stud reinforcement is used. Shear stud reinforcement is more effective compared to the stirrups or traditional shear reinforcement. It also increases ductility and drift capacity of the slab column connections. Also, there is one supplementary document for ACI 318-19, which is a ACI 352.1R, which is for design of slab column connections. And it requires further 25% reduction in concrete shear capacity for the slab column connections, which are not part of lateral load resisting system, but requires to maintain the vertical capacity of the column or connection when they are subjected to inelastic lateral displacements. So reliance on concrete shear capacity shall be less, and such connections shall be designed with reserve capacity or say with higher demand to capacity to demand ratio. Now, in ACI 318, some detailing requirements are given for column and middle strip reinforcement. If you see, it requires all column strip reinforcement to be continued, and it shall be extended in exterior support for at least 150 mm. I believe according to IS 1893, the perimeter beam is mandatory, and this reinforcement can be anchored in this beam for development length for better redundancy. This perimeter beams can be designed as stiff torsional member. Also, ECI requires that minimum 2 column strip bars shall be continuous, and it shall be anchored in exterior support for the development length. These 2 bars shall pass through the column column core, and splices shall be limited in 0.3 LN area from center of support, and it shall be spliced for development length considering the nominal strength of reinforcement. Any reduction in development length to account for excess reinforcement is not allowed for such reinforcement. This integrity reinforcement allows alternate load path, and it gives certain reserve capacity to transfer the load to the adjoining vertical element in case of punching failure or in case of loss of column. If you see, the detailing are also specified in IS 456 for flat slab. However, there is no continuous bar for column strip and also no continuous bar for middle strip. They specified certain curtailment for all the bars. No bars is continuous from the interior support. In ACI 318-19 and in IS 456 also, we required to concentrate the top reinforcement in effective width. This reinforcement is generally designed for the flexural part of unbalanced moment. However, in ACI 318, some minimum requirement is also specified. This reinforcement is very important to prevent the flexure-driven punching. When the reinforcement is very less than the specified value, it can yield, resulting in sliding along inclined cracks, which are formed at shear stress well below the shear capacity of connections. Here, in such case, with low reinforcement, the shear capacity, the contribution of punching shear reinforcement in shear capacity will be very less or nil. So, but however, it can help to allow some plastic rotations. So such requirements are not available in IS 456. As we discussed before, ACI has a requirement for integrity steel. There shall be minimum 2 column strip bars, which shall be extended in support for development length. The supplementary document of ACI on slab column connections have very stringent requirement for this integrity reinforcement. This reinforcement is worked out considering actual factor load on panel, considering the panel dimensions. And for evaluation of this reinforcement, a model has been considered where punching shear reinforcement has occurred, top concrete cover is removed, and bottom bars are bent at 30 degrees from the horizontal. This requirement may be very stringent, and the reinforcement required by this clause may be very high compared to what is required from ACI 318. And it is also recommended to have this reinforcement for beam column connections where the depth of beam is less than 2 times the depth of slab. Canadian code has correlated shear with the integrity reinforcement, and the slab reinforcement, which is connecting the slab with column perimeter, shall not be less than 2 VSE by Fy. Here VSE is the shear transmitted to the column. We don't have any such requirement in IS 456. Eurocode requirements are similar to ACI 318-19. It also requires two column strip bars to pass through columns in each orthogonal directions. So this our priority shall be to prevent the shear failure of slab column connections. But when the demand is extreme, like in event what we are discussing today, there must be some integrity reinforcement which can provide alternate load path and some reserve capacity to transfer the load to stiff adjoining elements. Also, the adjoining elements shall have reserve capacity for such undesirable events. So, thank you all for hearing me and for your valuable time. Thank you. I request Dr. C.V.R.Murty sir to continue with his presentation. Thank you.
Good evening, ladies and gentlemen. Once again, I will focus the next few minutes on provisions to prevent collapse of buildings in flat, especially I'm looking at flat slab buildings. What is important and what is urgent will be our focus now. My preceding speakers have emphasized the importance of the contributors to preventing collapse, which is good stiffness, sufficient strength, and adequate deformability. And I would also like to see that this is an opportunity to learn and to implement those features that are good, not just in our document, but also in all the international documents. Ultimately, the focus for us always has to be safety. And when I say safety, I'm looking at life safety as a bottom line, no nonsense, no compromise situation. I must also take this opportunity to mention that IS 456 is under revision. And in fact, this is the 5th revision that is underway. And we are doing this revision almost after about 40 plus years, 43 years. And this is a wonderful opportunity for us to see what is good in terms of the provisions required to ensure no collapse, especially in flat slab buildings. So the meeting today is actually very valuable in trying to carve the provisions for the new version of IS 456. But there are numerous building structural systems. And when you look at flat slab systems, obviously, they don't fall into the second two categories, but they largely are in the first category. And from what we hear from Professor Goswami, we seem to have a concern that how do we manage to do this when we don't have the beams present with just the help of slabs alone. When I look at the internet literature available on collapse of buildings, I get this picture, very interesting picture in which about 7 cases of pancake possibilities are there and about 4 cases of lateral collapse are there. But there are many other localized issues also highlighted in this slide. But my take on this entire slide is that none of these is actually acceptable for us. And that is what I will say as the backdrop of all that. What I'm saying is there is no way we can allow any building to go through any collapse of whatever kind. Even if it means that certain structural systems are not good and we should drop them, we'll definitely drop them, right? So here is where we need to understand the importance of the loading that we are imposing on this, on the various buildings. There are 2 types of loads, force loads and displacement loads. As you can see on the right-hand side, displacement load is not taught in colleges in a normal sense, but just in passing about settlements, foundation settlements is just one activity that is normally discussed, but the rest of them are done in passing, at least in India. And so I'm looking at the fact that when you look at flat slab buildings, all the displacement related loads are going to cause a lot of worry for us. And that is where we need to strengthen our provisions to make sure that these issues are considered. Let's look at the displacement loads a little more carefully. We're looking at temperature as a possibility, heat and temperature. Second one is elastic shortening when we make certain members too small. And also creep and shrinkage come alongside that. If you have overstressed a column, and then so you can get into long-term creep effects as well as shrinkage because of certain choices of materials also. Settlement is another matter that will be a worry for us. And of course, lateral actions of earthquake shaking will be a displacement load that we need to be careful about. All the 6 of them will be our worry. Now, once again, to emphasize what Professor Goswami said is that it's convenient to have an elastic behavior, but yes, that can be expensive. So one allows a certain amount of inelasticity. And so we have a design load, then we have the end of the linear range where damage begins, then we have the maximum load, and then finally the building collapses. What we are interested in is now to estimate delta max, which is actually giving us the range of the inelastic behavior. Now, the entire game of going from a linear behavior to nonlinear behavior is possible because ductility is available. If this ductility is not available, this green deformability is not available, then you cannot do this inelastic action at all. And you have to resist everything elastically. Now, we also notice that we have two other factors that contribute to that. One is redundancy, and then the other one is overstrength. Let's look at the system in hand, which is buildings with flat slab. And we see that they don't have ductility, they don't have redundancy. And the only thing that could have been there is overstrength. But if we compromise on the size of the column and make them very, very slender, then we are also losing out on the overstrength that could have been possible. So on the whole, we are looking at a system that doesn't have most of the desirable features, and hence this deformability or the warning before it goes into collapse action is not available for us, and it will be rather brittle action for us. So the aim of all design provisions related to buildings and safety will be to uphold the virtues that Professor Goswami mentioned, and by all means prevent collapse of buildings. And especially when you have flat slab buildings, this will be our key worry. Let's look at the current design provisions in the Indian standard. The first two are geometry and openings. Geometry, of course, sort of defines the sizes of the heads and the drops that we can have or we should have. And on opening side, it talks about the proximity of openings to columns and thereby their impact on the critical section for shear, especially for punching. And the next provision that we have is the one on design for shear. And of course, we understand the critical section. And if we have axial load only in the column and no bending moment, and if we have bending moment only and no axial load, and then if we have both of them, we know how to calculate or how to estimate the shear stress demand on the structure, and then make it that this stress demand is less than the capacity available. And the provisions which just now we heard from Hemal Mistry, that he was talking about the permissible shear stress values there. Now, the fourth and the fifth are related to design for moment and also the slab reinforcement. This is a classical information which we have been adopting: middle strip and column strip. We have bending moments and how to estimate them by two methods that we have for ourselves. And then, of course, finally, the reinforcement, slab reinforcement that we are providing. As Hemal Mistry said, there are concerns about the way we are providing the reinforcement as per our IS 456 current edition. And so we need to definitely revise those clauses. On the whole, when you look at a flat slab system, we don't take solace under the provision of, by providing drops and heads. These are only local effects that we are looking, but the global issues are still at large. The global issues are that even for little lateral unsymmetry, we will be able to, we will be required to have large amount of stiffness, and so that is not available. We don't have redundancy for redistribution. Just in case a member has some distress, it can't take help from the other members. And of course, the way we are loading this large columns, large loads on small column areas, even ductility will be a worry for us when we go to the apex of the PM interaction diagram. So we need to bring in global aspects into the design provisions in the time ahead. So what is the aim of design provision? The new set, I'm saying, is to uphold all the virtues that we talked about just now, but also ensure that, say, lives are saved. It is heart-wrenching to hear collapse of a building when we lose people. And so I think we have to use this as an opportunity to resolve that we will not have provisions that can cause such collapses. So when you look at columns and walls with flat slabs as one unit, I think this is where urgently we need to make sure that there are basic features which are like configuration related items, which we have to guarantee in our new provisions. Second is the focus has to go on analysis of the combined structure with columns, walls, and flat slab, and not simply rely on our direct design method or the effective frame methods that we have in the code. The reason why I'm saying this is that we don't read the assumptions. We just use those methods indiscriminately for all cases. I think if you read the assumptions, it's pretty sharp and strong, and we would not have built many of these that we already have. The critical part is, of course, to bring back into focus global issues of overall stiffness, overall strength, and overall deformability of the building. Even if it means that in some cases we will not be able to build flat slab buildings, I think we should bite that bullet because the consequence of collapse is not acceptable to us. When we look at future design provisions, I have 7 statements to make. First one is regulated use of undesirable features. That means that if lack of grid is something that we cannot handle, we will have to say so. And floating columns, small size columns, poor lateral stiffness. I think these are loud statements which we have to understand that if the grid is not available, then the geometry and the deformation is not going to be acceptable. If it is small sized, you will see undue stresses. If it is floating columns, you will see undue behavior. And if it is poor lateral stiffness, you will see no help coming even under vertical loads, right? So configuration and desirable collapse mechanism is our target. So we will not be able to tolerate some of these items. We have to write more explicitly than as mere assumptions in the explanatory notes, but they have to come into the main clauses themselves. The second statement is about combined analysis. We are doing largely linear analysis, and hence when you look at a system that is likely to go into nonlinear behavior under temperature, under elastic shortening and settlement, and lateral shaking, we need to have a lot more constraint on the use of this system, especially checks and balances that are required, and checks and balances from the point of view of overall stiffness. So the geometry of the structure, symmetry and spacing of the spans and so on, material, high grade or low grade, and then boundary conditions, especially related to the support. Third item is related to design. First item is stiffness, and in that vertical, in all of these cases, we want to make sure that the vertical stiffness is assured. And columns are the ones that will keep us in trouble if we are trying to be miserly about it. Important point is settlement cannot be handled by structural solutions. The settlement has to be sorted out before we get the structure on the strata. And so we have to fix those issues or understand those issues. And only if it is possible to accommodate that in structural design, we should consider that. Otherwise, we should even go to the extent of dropping that site, right? So geotechnical investigations required should be our focus. Design stiffness in the horizontal direction. Again, earthquake shaking is our issue. By providing structural walls, you can choose a uniform grade and large cross-sectional sizes and good connections and make your structure survive. Because if you are looking at the load deformation curve or the stiffnesses of the buildings, building without flat slabs don't have any stiffness, and that is where any honorable stiffness, and that is where we need to bring help, and the help will come in the form of walls into these new provisions, in the new provisions. I hear a lot of concern about the use of a very stringent requirement in IS 1893 of 0.1% lateral drift. But if I look back at the research work done by Professor Durgesh Rai and a student at IIT Kanpur, they do say that the lateral drift based on about 300 or so experimental data tells us that we don't have much capacity in flat slab buildings. And so we have to keep the lateral drift as low as we can see as 0.1%, right? And the next item is design for strength, both horizontal and vertical. A key question that I have is if this is the expression for design for axial load, where concrete contribution is 0.4 FCK, I do see that the axial load, axial stress ratio that we calculate simply by dividing axial load with the FCK and the area of cross section of the column that should be far less than 0.4, but somehow we seem to be shying away from taking that decision. Maybe this is the time when we look at the collapse, we don't feel comfortable that we have liberty or luxury to go with a larger number now. Both Alpa Sheth as well as Rupen Goswami emphasized on the PM interaction diagram. I'll reiterate that it's time to get closer to the balance point and not go unbalanced at a much higher elevation. That will be tough for us to handle. So the design, the sixth item is detailing, especially integrity steel, which we need and we don't have right now, and that is our worry. We need to put in some stringent requirements for integrity steel. When you look at the deformability issue, whether it is vertical load or whether it is the horizontal load, there is a need to understand the collapse mechanism, and only then you should be able to sign the drawing for construction. Without preempting the collapse mechanism, we should not take chances on these very special structures which are being built across. I'll close this discussion today by saying the key virtues of flat slab buildings are highlighted. It is strength, stiffness, strength, and deformability. And we need to protect that or ensure that in our buildings, especially the inelastic range we need to understand. But what's very important is, while we always have been worrying about materials, sections, members, and detailing, we have not worried about the return path. And so we are not guaranteeing to our users exactly what is the structure we are giving them, whether that will collapse or not. So the closed loop design strategy has to come, especially for this kind of a structure, which is hinging all its, putting all its eggs in one basket, which is the vertical columns, and that too are, dimensioned rather miserly. And the same, of course, is valid for horizontal actions also. We should protect both of them, and give a closed loop method should be mandated in terms of making sure that the collapses do not occur for us, right? Another important point I want to mention with this flat slab buildings is, while you might hear all these words in the market, I must also mention here that repair is definitely not retrofit, but even retrofit is not so easy to happen in a flat slab building. So if you make mistake at the beginning, there is no way to correct that, right? You might say, no, I'll shore it, I'll jacket it. Then you have to vacate the whole building, and slowly the popularity of the system will vanish, and the users will again go back to the traditional system. And it's important for us to not have it done any other way, but only the correct way right at the beginning itself. When you look at structural systems, the whole load of them are mentioned for exterior structural frames and systems, and the interior ones also. What is important is flat slab doesn't show up there because flat slab is an element and not a system, right? And the use of flat slab has to be done more judiciously and not indiscriminately, if you want to say that we are protecting people and not allowing collapses to happen in them. I think over the years, designers across the world have learned so much, and many of the failures also have taught us so much, that I think we need to rely on the traditional knowledge and go from untruth to truth, and from darkness to light, and from life to eternity. Only then we can guarantee that the buildings will survive their design life and not go faster than that. Many times we shy away from taking the early steps. I think it's important to be bold and take some very difficult decisions for the good of the nation. And that is what I want to say, is that if you're looking for an India in which no collapses should happen, if that's your dream, I think it's possible for us to build a strong Indian standard in the years to come. Ladies and gentlemen, I'll stop here by thanking Structural Engineering Forum of India for the opportunity to speak here today, and thank each one of you for your kind attention. Jai Hind.
So thanks very much, Professor Murty. I think we've had lovely presentations. Sanjeev, if I may bring you in over here, is it time for us to go into the question and answer session? Because I think we have about, we should close at 7 o'clock, Professor Murty, Professor Rupen, yeah? So we have about 20 minutes, 24 minutes to kind of respond to the question and answers. If we can read them out maybe, and shall I do that? And maybe Professor Murty and Professor Goswami and Hemal, if you would like to come in wherever you would want to, that would be good. I'm just going to read them as they are. I'm not filtering anything. So I'm not going to read out the comments. I'm just going to ask questions. There is a question from Mr. C.V.R.Murty, and he's asking for external flow over a flat plate. What is the boundary layer thickness? Is continually increases. I guess you. Anybody wants to take that?
The question is not clear actually. What was the intent? Yeah. So
yeah. Okay, I'll go to the next question. Alok Bhaumik is asking, what was the trigger for failure? I think, Alok, you know, as what I had shown, the design of the column is marginal, and then corrosion we have added to that. And that is, you know, our very initial observations. We will have to wait for, you know, a more detailed investigation, which will have access to materials and all of that. But at least the numbers, when they were crunched, we just felt that the column design was extremely marginal. Yeah. Okay. The next question is steel overlapping integrity mentioned in IS codes? You're both unmuted. Yeah. Okay.
Let's bring Hemal.
Yeah.
Hemal, you can turn on your video, please.
I'm not able to turn it on.
Okay, go ahead. Go ahead and speak. Yes, we can see you.
Ma'am, can you repeat? I was not able to hear.
Is there integrity steel in the Indian standards?
As I discussed, presently we don't have any integrity steel in Indian standard. The column strip reinforcement are not even continuous, and middle strip reinforcement also have some curtailments. So presently we don't have, but we should not wait for the code, and we should start using some provisions from international standards from now.
Absolutely. Great. Okay. The next question from Mr. C.V.R.Murty is, can pre-stressing cables work as a tie and reinforced concrete and consider as a tie force indirect method for resisting building progressive collapse? So I'll bounce it off to Professor Murty.
Yeah. Yeah. I pray that pre-stressing cables here are alluding to a lateral pre-stressing action in the slab. And so I'll request Professor Goswami, if you have any slide that we were discussing, do you have that? Can you show that slide and maybe describe it?
Is it seen?
Yeah. Go to the presentation.
Yes.
Go ahead.
Yeah. So the issue is that we treat this PT system in isolation. I mean, when we do the structural analysis, we really don't consider the PT. But imagine you have the columns and then later on you do the PT, and then what it does is it kind of pulls all the columns together. The question is, do we consider the effect of this on the column, the additional moment that would be generated? So I think we need to, migrate to a more holistic structural analysis rather than just doing the design of the RC part independent of the PT part. So this is an important thing that I think we should consider.
I think that's a very good point. Yeah. So, but his question was actually something else. He is saying that since we were talking about the collapse and integrity steel, I think what he's trying to allude to is, what about the pre-stressing cables? Can they work as the integrity steel?
Yeah, see, the pre-stressing cable by itself is going to be healthy and happy, but the support fellow who's supporting that cable is not going to be so happy and healthy. So right. I don't think that there will be positive gain, but you must recognize that every pre-stress is causing additional compression in the concrete, and that is taking us more towards the apex point. And that is why it's not the favorable situation to be in.
Right, right. So this was a question we all had expected. And can we say that if the codal provisions that were missing in the 1970s for the design of the tower, would it avoid the collapse of the tower? If I'll put it differently, that if this building had to be designed by ACI 318, even 2014, 2018, would it have survived?
Yeah, I mean, I don't know, maybe anybody else can say that also, but what I am looking at is, it's not the provisions. It is the engineering that we do with the provisions, actually. Provisions have always been there, and many standards are really nice provisions. But are we, if you dimension the column so small that the bars, so-called specified bars, cannot go through that, then how do you blame the provisions for it, actually?
Right.
Structural engineering is beyond provisions.
Right.
Structural safety is beyond provisions. It is about the intuition a design engineer can have. It is about the sense of feeling that the structure is a live facility, and that it is breathing under these different loads and force loads and displacement loads, and that the load paths, you can feel the load paths. If you can feel the load paths, I think then you'll understand that provisions are not required. For all the virtues, you can't write provisions, right? There are many more virtues that for which provisions are not available, but very desirable. Are we willing to practice that is the key question.
So let us turn around this question and ask another one. You know, as we saw in Champlain Tower South, the percentage of steel in the columns was as much as 5.9%. Now the question is, if one mandates that you have to restrict the percentage of steel to 4% or 4.5% or some such thing, is that going to be helping to, as what Professor Goswami said, that you do need to have certain sizes, minimum sizes of these column elements. Do you think that would be possible to?
Yeah, I mean, maybe I shouldn't take all the questions, but I'm saying one of the things that I'm seeing is that one provision doesn't make the building safe.
Yes.
Right? I think every bit helps. In the process of guaranteeing Professor Goswami that the structure has the deformability, that process is a very tedious process, an arduous process, and every bit helps. Column size is one item, right? Dimensioning, yes. Go ahead, Rupen.
No. So I just want to add one thing. See, reinforcement is not going to help you with related to stiffness. It can give you strength. It's not going to help you in stiffness in any way. So that's the first thing we need to, there's no point in putting in reinforcement after reinforcement and then thinking that everything is going to be fine. So that's one thing that, a thought came to my mind related to the previous one. So one is, of course, as practicing, as engineers, we always look at code compliance, but then there is something beyond that, what we call as good practice, and safety is beyond all this, basically. So we need to remember that.
Yeah, also I'll say this, that I have a lot of literature is there which says that the horizontal member should have a L by D ratio about 12 to 14 for it to form plastic hinge action, right? Now, if you look at the L by D of a slab, if you're taking even the modest 6 meters and you go with 250, that number is a very large number actually. I don't know how to calculate, but it's a large number. That's what I'm feeling. But I would say that the slabs will not, flat slabs will not give us those plastic hinges, that beautiful ones that Professor Goswami was asking. So dimensioning the member is the first part of it, and that guarantees stiffness, and stiffness means you're attracting lesser deformations and thereby lesser stresses are induced in the structure. That is the first step. And then once you have stresses, then there is the issue of strength. Then the steel comes into picture. But the first item is missing, the second has no meaning for discussion. Right? You have to go in that very sequence in which Professor Goswami showed: stiffness, strength, and then deformability. If you don't maintain that discipline of that order, then it's not going to be a successful structure.
So just to add to the dimension part, so there has to be a absolute dimension, first of all, a minimum, maximum, absolute dimension, and then a relative dimension. That's equally important, because it's these elements, different elements were going to play with each other in terms of stiffness and strength. So if one element is too flexible, too small compared to the other, it's not going to help. They will not be able to interact with each other. So relative dimension is equally important.
Yeah, Rupen, Professor Goswami, it's an important point you've said. If I had to just extend it, when this was built, probably we were not in engineering college also, but I remember my father being a structural engineer. When he taught me flat slabs in the late 80s or early 90s, he would tell me even at that time, he said the first thumb rule for dimensioning your columns would be 1/10 of your span. That would be like the most basic. And then, of course, that's how you start. And then, of course, you go further. Now, I was just looking at this building in the light of what I remembered from last 30 years ago. And, I'm just thinking that you're looking at a 7-meter span, and you would think that you need 0.7 meters. And here you have 0.35 meters. Right. So something was a bit off in terms of the dimensioning and the proportioning of the columns. And unfortunately, now what has happened is, and which happened over there in the 80s, is that the use of high strength concrete, has been making the sizes smaller and smaller. And what is happening is we are conflating the issues of strength and stiffness. And we are not realizing by doing what we are doing, we are reducing the stiffness to a point which is a matter of great concern. And I think this building collapse is going to be an eye-opener for the whole world, and especially when this has happened in the first world, where such incidents are a complete no-no. I think it's going to make people ponder. And if I'm not mistaken, my guess is that there are going to be very drastic changes in codes across the world. That's my guess of how it is. I want to throw this next question to you, Hemal.
Yeah.
The question is by Solomon Abebi. I'm sorry if I'm pronouncing your last name wrong. Forgive me. The question is, both in ASEAN and Canadian code, steel integrity is well represented. But in IS 456, the presenter tells us there is no availability for such cases. So my question is, does IS 456 consider other alternative ways? I know what your answer is, but I want you to say it.
Presently, we don't have such integrity reinforcement, but as I told before, we can adopt certain provisions from international code. And even if you see in the collapse building, at that time there was no provision for integrity reinforcement in ACI code also.
Yes.
But after, say, in Ronald Point building, which is in UK, it was collapsed in 1968. And the requirement of integrity reinforcement was there in 1989. So it is up to us that whether we should follow it only if it is mentioned in code, or we can adopt it from somewhere else for the safety of structure.
So thanks. Now, there is very interestingly, we have Mr. Benjamin Moore, who is an architect. You're not a humble architect. We are the humble engineers, and you are the master architect. So, so the question is, I would be interested in knowing what repairs would entail. If the rebars are rusted and corroded, can it be replaced entirely? Must it be replaced entirely?
Yeah, so let me say this. If I have a flat slab building and I'm suspecting corrosion, I should know how much is the extent of corrosion. And if I have to then open the cover of all the columns and replace all the bars, what I learned in another collapse of another building is there was a masonry structure. It had plaster on the outside. And somehow it was decided that they will redo the plaster. And the moment they removed the plaster, the masonry structure came down. It's a historic structure. So I'm not comfortable unless I know the entire story of what is the extent of corrosion in the entire structure. If I know that, then only we can take a very, very pragmatic decision which way to go. Even if it means the difficult one, we will have to take that difficult decision. But if it is extensively corroded all stories, I don't think we need to go into that building.
So, the example you've given is also very interesting, Professor Murty, because, and this was what I was discussing with Hemal yesterday. And, the conventional wisdom is that the dog wags the tail, but very often the tail seems to wag the dog, as in the example that you gave, that sometimes the building, is just being held by the breadth of a hair, and that could be the plaster, right? So
another worry I have is in small sized columns, if you lose the cover, it is 30% or 40% of the area. That can put your numbers off. The one that you showed on the axial stress ratio can really shoot up, and that is going to be even more embarrassing.
Right.
That is where the trouble will begin for us, brew for us.
So the next question I'm going to put across to Professor Goswami: has the stiffness of transfer girder helped in resisting collapse?
Well, the west part, I'm not sure if we can make that conclusion. At this point in time, because those transverse girders are, of course, supported on some columns. Fortunately, those columns have not given up, and so they're still
they were
standing.
much larger columns. They were much larger. So
eventually, I think it again boils down to the the performance of the columns and not so much of anything else.
Right. Okay, we have a lot of questions. I'm sorry, ladies and gentlemen, we're not going to be able to. I am going to skip the PT questions today because we hope that at some point we will be able to, have a session on PT slabs. But unfortunately, today is not going to be that occasion. So one question.
In any case, we don't have any current provisions. So legally speaking, we should not be building those.
Right. Okay, Pradeep Joshi writes that time-dependent creep and shrinkage provisions for flat slabs are missing in all codes. Kindly guide.
Yeah, definitely. I mean, this is something that we need to bring in quickly into the analysis part first, and then into the design part next.
Yes,
definitely. No question about that.
Upcoming Euro Code 8 in 2024 is considering flat slab as a primary element. Previously, it was considered as a secondary element only, but in India, flat slabs are seen differently. Kindly guide. I think my answer would be that the 2024 code will change quite drastically post this collapse. I don't know. What is your opinion?
No, definitely. I mean, how can I say that flat slab, which is so thin, is the primary element, and that I'm asking for it to transfer the forces? It can't take axial load because it will buckle. It can't take bending moments because it doesn't have the L/D ratio required to form plastic hinges. So I don't feel comfortable defining it as a primary element. It is not for me. I mean, every country has a right to say whatever they want to. Let them say. Why should we, say anything about them saying it? Let's look at it ourselves.
The next question is, can we say complex designs showing so-called modernized look be minimized? And I can take that if you want. I think Mr. Bishwajit Singh, that is not what we're trying to say. What we're trying to say is complex designs which don't follow the conventional wisdom of robustness, integrity, and the basic elements, the basic virtues of strength, stiffness. The conventional ones require a lot more rigorous analysis, design, peer review, and the whole gamut of requirements will be such that unless your client is ready to invest 2 or 3 times what he would have normally invested in the design of a building, I do not think that you are going to be able to do justice to the design that is required of the client. Anybody wants to give?
Yeah. Let me add here that, see, if you do the closed loop design, then you will know your problems yourself. You don't have to go to the peer reviewer at all. You can do it in-house. You can find all your mistakes, all your errors yourself. Nobody need to come in. In fact, I would say the first thing is, if you do your modal analysis properly for 1 week, you sleep with that modal analysis and understand the results properly. You know where you have extra stiffnesses, where you have flexibilities. It will give away all the answers in the analysis stage itself, not going to design. And then second order is to go and do the closed loop design and make sure you identify your own mistakes. Then you will know modern design, look, architecture, all that is fine. Only thing is subjected to classical discussion of load paths. And this closed loop method is actually giving you that understanding of load paths. Proportioning, load paths, strength ratios, all that, the strength hierarchy, it will give you that understanding.
Okay, now one question is high-rise building by Mr. Mohammad Zunuren. High-rise buildings without flat slabs are more safe than buildings with flat slabs. That's, anybody wants to say it? I mean, it's
No, I don't think I want to make a statement here on this subject. No. It is improper to give such a sweeping statement in either direction. I think my answer to all these extraneous and extraterrestrial questions will be closed loop design. Do closed loop design, you will know your mistakes. Whether it's sufficient, good, bad or not, closed loop design is an answer for you. And nonlinear tools are available. Even whatever level of tools are available, you can still use them and get a headway on that.
This question is, the question from Gagan Patitar is to Rupen Goswami. I mean, I'm passing it on to Professor Goswami, that, you know, if you are in a zone 2 earthquake area, you know, can you design a 4-story building as non-sway frames? You know, for small buildings, does the effective length matter?
Well, zone 2, 3, 4, 5, I mean, we'll have separate, you know, detailed discussion on these. But see, the point is every element, it can be a small 4-story structure, but the element is how it is restrained at the top level and the bottom level, and what is the relative stiffness that adjoining members are providing. So that defines the governs the effective length. So those calculations still need to be done. Of course, in engineering practice, when you have done enough of those buildings, you know, you kind of develop thumb rules, just like one you heard. And so we can say that, okay, instead of going for detailed calculations, we can go ahead with some thumb rules. But, you know, at the end of the day, effective length still remains a valid, you know, entity in design calculation. So right. I'll just leave it at that.
The next question is, the building might have been designed as per ACI 31877. That's right. Were the provisions followed in the design? Mr. Stroke, Ms. Narayanan, we do not know. We have not checked it as per 31877 because, to be very honest, both myself and Hemal did try to access 31877, but, you know, obviously it was in the pre-internet era, so it is not easily accessible on the net. So we have not checked it. But my feeling is that some of these requirements have not changed very much over the years. Hemal, would you want to correct me? I mean, simple things like axial stress ratios and so on. Do you think that there has been a major change over the years?
See, if you see for the punching shear requirement also, the requirements are almost unchanged since from 1989 to 2014.
Yes. Yes.
There are some significant improvement in terms of, say, the depth or size factor in recent version. Otherwise, the permissible stresses always have remained unchanged. There have been certain improvement for PT regarding requirement PT, but that we are not discussing today.
Okay, right. So, but the short answer is we've not checked, Mr. Ms. Narayanan. So we have architect Benjamin Moore again, and actually I know the answer to this. I think I know the answer to this, and let me see if Professor Murty knows the answer to it. As an easily distracted architect, has nothing to do with our presentations, but let's still answer it because it's a fun question. As an easily distracted architect, I must insist that Dr. Murty identified to us the wonderful structure sitting atop the rock in the middle of a flat field. It's actually in the middle of a forest. Yeah.
Yeah, see, when I make cartoons, I will always choose the exaggerated deformation diagram for that. And you might think that I'm putting a rock and then soft soil and showing the contrast. I definitely want to show the contrast. But the bottom line here is, if you have a field, let's say a paddy field, and it's got soft soil, it's got settlements, and first you fix the settlement issue. And geotechnical engineers found so many solutions for that. Like preloading is one of them to reduce the consolidation effects later on after the structure is built. They do that, and then you can go ahead and build the structure, right? They do that in bridge design, bridge construction also. It's not that in paddy fields we don't build all these structures. We do. There is a certain level of engineering and maturity that we have to bring in through other disciplines. All problems cannot be solved by structural engineering. There are geotechnical engineers, there are hydraulic engineers who will come in and then give us their inputs and so on. Piping is another issue if you look at the western part of India. And so we definitely require everybody's participation. So the more complex situation, the more number of players in this design process.
So no, I think Professor Murty, you have not answered the question. His simple question is, what is that? Where is that structure in the world, which is that rock in the middle of a flat field?
Oh, that one is Sri Lanka. That is Sri Lanka.
Yeah, that's what. So let me answer the question.
Sorry about that.
Let me answer the question.
I took it as a technical question. I didn't think it.
No. So in my opinion, and I could be wrong, but it is a C.V.R. rock.
Yes.
Yeah.
Okay. Yes, it is.
Okay, great.
Sri Lanka, yeah.
So we've all got marks, some points, brownie points in general knowledge. Okay, the next one is Jaideep Chotalia. So I showed earthquake accelerated recorded history of some important earthquakes. What value of PGA and what directions were? Okay, this is not going to be answered over here. I don't know. These are non sequiturs, and I would really appreciate everybody just ask questions related to what was presented or the topic under discussion. The C.V.R. rock question was a good one. If there is general doubt on the strength capacity of buildings designed with flat slab when it comes to resisting lateral loads. Is there a general doubt on the strength capacity of buildings designed with flat slab when it comes to resisting lateral loads?
I think it is demonstrated by so many events, including earthquakes. So we don't have to.
I think one of the things which Jade Sereno may benefit in is that if you look at just do a search, an image search of the Mexico earthquake of 1985 or the recent Mexico earthquake, which year was that?
2017.
2017. I think you will get your answer. You will get your answer. Yeah. The next question is from Ibrahim Saliba. Hi. Were there any expansion joints or construction joints separating the three parts that collapsed? No, Ibrahim, there were no such things. The building stood 40 years. If the column design or slab detailing were not adequate, why it was not observed? That's exactly what we are saying, that compression failures are sudden and brittle, and they do not give warning. So basically, and that's why the PM diagram was being shown that, when you're going to be above those, you saw those lines, those F5 lines, and now you're way up there, you're just going to get compression failure and nothing else. And that's going to be happening without warning. And anybody would want to add something to it?
Ma'am, and also the corrosion of reinforcement and deterioration of concrete might have reduced the strength to the extent that it collapsed after 40 years.
Very right, very true, very true. That's also a very good possibility. It was already a marginal design, and then over 40 years, it's right on the sea waterfront. So there must have been a lot of corrosion, perhaps, and that was, it's not my conjecture. It is what is given in the survey reports. So that could have been also an, a catalyst for what happened. Next question, is it possible to have a provision which requires a brief review and approval from an independent consultant in case of flat slab system, considering the severity?
This is independent of the original design. I think that's a second order issue.
Yeah,
but
that's
the design itself has to be robust.
Yes.
And then this is anyway required for all structures, and if the country doesn't have it now, we will have it soon. But
yeah, but I also want to point out that I do a lot of peer reviews myself, but I also want to tell you that sometimes there's a danger of a cabal. I pat your back, you pat my back, and we have to be very careful in how do we bring in systems and procedures in a country like India to make sure that the peer review is actually giving you what you want in terms of peer review. I think that there are some clients who have very good systems in place where they are themselves overseeing the whole thing, but not every client will be having such a system in place. So I think that that's more work in progress and can be talked on another time. Architects are proposing flat slab structure for G+1 villas to have beamless ceilings. Is it recommended? There's one more thing which we have to explain to people, that a beamless slab need not be a flat slab. You can have a very large span slab. It can be as much as 7 meters by 7 meters, you know, and or even 8 meters by 8 meters. But as long as you have designed it and on all 4 sides, you do have elements, you know, whether it's beams and which are supported on you know, columns and whatever. I think that, you know, let's be very clear that we are talking about flat slab structures here, where you have the system that we are seeing, and where that one missing element, as what Professor Murty said, the beams do not exist, right? But the issue is that a large span slab with beams is sometimes quite all right, and that could give you a good option to a flat slab building where you don't have any beams. Anybody wants to say anything?
Yeah, no, we can go forward.
Okay. So, Jinal Doshi, even with the buildings with flat slabs have good ductility and drift capacity up to 3%, provided that we provided good ductility, then why aren't buildings with flat slabs with shear brace was allowed in structures with higher drift demands? Is there any plan to include ductile detailing? I don't know. I think, you know, Jinal Doshi, you may want to read the codes. Okay, our Indian codes are very clear that the flat slab, the column strip and the column will not be allowed to be taken as a lateral load resisting system. And I think that, you know, it's already codified. So I hope that answers your question. Prajwal Samarth, if the slab is resting on the wall and columns, but I have to remove that wall, what would the provision as span is about 14 feet? Okay, this is a special question. You know, you can ask it offline. Can setback columns be considered as lateral load structural elements?
No, certainly they're not the good ones to take in.
Okay. Mr. Musab Bhatt, does seismic factor have any role in the collapse of Champlain building? No. Can we consider hidden beam with same depth to avoid less of redundancy of this flat slab? No. That's sleight of hand trying to call it. There's nothing called a hidden beam. Hidden beam is an imaginary concept. Everybody agrees with me, or is there anybody who has a different opinion?
No, if you want to call it a beam, it must have at least a minimum L/D ratio. If you are giving that, then the beam is full thickness of the beam. If you provide the slab, I have no issue. I know a slab which is 5 feet thick, no problem, right? So that is fine.
Yeah, the next question is, what is the definition of integrity steel? So presently the integrity steel is the steel. You want to have a certain continuous reinforcement even in the bottom, okay? And that is presently what is called the integrity steel. And that is, you can refer to ACI 318, you can refer to Eurocode 8, right? And, you know, you can refer to the Canadian code. Okay, the next question, once the concrete gets cast in the structure and we get the result, okay, no. Is it healthy to mix 2 or more design codes in a single project?
No.
I think you need to, okay, so I think the answer to this question, Mr. Solomon, is that you need to follow one code in its entirety. If that code, in your opinion, does not have, is unconservative in certain issues, or is silent about certain issues, you may refer to another code which is more specific, which is more articulate, but that code, you cannot give provisions which are less than what is the mother code you are referring to. You can make it.
And so we cannot directly adopt the foreign code requirements, because they, ultimately at the end we will get a solution, but the flow of design, say if you compare ACI code, they use the rectangle stress block, they use cylindrical strength, they have different partial safety factor for loads. So and if you see, even for the column design, they reduce the design strength to arrive at the size of column. So basically the axial compressive stress will differ from sizing of column. So you cannot compare, take any provision from foreign code without any modification to comply it with Indian code.
Let me add one more thought here. When I look at any standard, it has 2 parts. One is quantitative part and another is qualitative part. Qualitative part are all the good features that every structure must have. And so there is no harm in considering the qualitative part, which is good practices. But when it comes to quantitative items, empirical expressions, exactly what Hemal Mistry said, that they are deriving those empirical expressions based on structures designed as per certain provisions which have load factors and strength factors and all of that.
Absolutely.
So the qualitative part you can take, but not the quantitative part.
Yes.
So Abhijit Avantukar is asking a question. What is the role of leakage and corrosion noted at the swimming pool? I'm going to make a very reckless statement, but I'm going to say that the leakage and corrosion at the swimming pool was not a smoking gun. It was a red herring. Okay, I'm not very convinced that it had anything to do with I mean, it could have been part of, but if you have noticed, the swimming pool is very far away from the main structure. So that's our personal opinion, but anybody wants to add anything?
No,
nothing.
We don't have enough information.
Yeah. So but there was corrosion. I'm sure that definitely made the increase the vulnerability, and it could have been a catalyst, but it was not one of the main primary reasons. Which code should we follow for retrofitting?
Retrofitting of which structure?
Yeah, exactly. So if the result of this test is not up to the mark, what step should I take as an engineer? Okay, I don't think we understand that question. As the material engineering advances, there's always use of smaller cross sections. Is the idea put by panelists to restrict the use of high strength materials?
No. It's not about that. You use any material, but give us the final answer that it has those. Goswami was asking.
So the small point, Mr. Murtuza, we are saying is that, again, I'm repeating what I said, like a broken record, that do not conflate strength with stiffness. Newer materials, stronger materials will give you higher strength, but you still need the stiffness. So if you're going to go on reducing your section, see, stiffness is actually driven by the parameter of geometry. Right? So if you're going to make smaller and smaller sections, then you're going to reduce your stiffness. So that is a very serious problem. So there is going to be a point of diminishing returns that, higher and higher strength materials are really not going to help you to build safe buildings. Right? Okay. Mr. Benjamin has come again now. Okay. Let me just see how many more questions we have. We do have a lot of questions. What am I supposed to do? I think there's just too many. There's just too many.
Okay, take the last 5 questions.
Okay.
And 19:30 is the stop of the program.
Yeah, okay. The fun part is then just to read some nice comments saying some good things about any of us. Considering the small, okay. If we retrofit the structure as we calculate increase in capacity of the structure. I believe there's an indoor swimming pool at the lobby level. So the structural drawings do not show a swimming pool at the lobby level. There's an external swimming pool. If there is something which was done later, the structural drawings don't show it. Can we design a flat slab with small amount of rise? Okay, I'm not going to answer those questions. Retrofit, there are lots of questions. Okay, Vaibhav Varule, I'm going to acknowledge you because Vaibhav is my colleague at the office. There's a suggestion he has made. Indian standards should also present minimum steel and concrete consumption indices. No, Vaibhav, that would be too prescriptive. We want to have let everybody have their independence and free thinking. What he is trying to say, I understand. What Vaibhav is saying is this will help us in convincing the clients. Else the clients then sometimes go to other structural consultants who might be ready to cater to the client's demands. So I think this basically what he's talking about is the race to the bottom that is happening right now, and it is the elephant in the room. And we're all part of the whole thing. And Vaibhav, I know what you're saying, but there'll always be enough takers for good design. And I think that failures like this do end up being wake-up calls for a lot of people. What is the role of the 6? Okay, are there any? Gautam Acharya is saying for tall buildings, interstory drift to be checked for factored load, but shall it be scaled response or unscaled response as per IS 1893 in dynamic loads? Not directly related to this, but I think we've already given an amendment to this, Gautam, and Professor Murty, am I right? We've given a clarification. So my recommendation to you would be to just look at the latest amendment of the code, and you will see that whether the requirement of factoring is required, scaling is required or not, and it really helps you just as a hint, I will tell you. Compression shear wall should be below 0.4 FCK. Very important question. We have not, that is not talked about in the code that, we've given all the requirements of columns. What is sad is that you have nowadays shear walls which have, compression stress of greater than 0.4 FCK. So that's something which Mr. Akshay Naik, that's a good point. And I think the code committee is, I believe, looking into it. Okay, this is a feel-good comment by Benjamin Moore, and so I'm going to say it out. This is for Professor Murty. I appreciate Professor Murty's consideration of the most difficult questions in the long run, no matter where those questions lead us.
I'm just wanting to add here that as I'm getting older, I'm putting myself in the same building that collapsed, and I'm saying at the end of the road, if I spend all my earnings and then buy a house or an apartment in a building, and that building will take that fate, then I think old people don't deserve that.
Yes.
People deserve that.
Yes.
Right? No human being deserves it. I think we need to respect life as the fundamental, dignity. And every constitution of every country will ask for that. And I'm also asking for the same as per Constitution of India.
So this is a very interesting question. This is by Julie Mark Cohen, and she is Dr. Julie Mark Cohen. She is a PE, and so by the way, we do have quite a few people from the United States, and one of the reasons is I have some friends who are architects and engineers there, and they were very taken up by the fact that we were doing this talk on the Champlain Tower, and just out of curiosity, I think a lot of people have been participating in this. So Dr. Julie says in the United States, there are at least 3 things that have resulted in the construction of hundreds of flat slab buildings. Developers want to construct buildings at minimal cost, and we saw that, right? Floor to floor height is 8 feet 10 inches. Out of that, 8 inches is your slab, 2 inches is your floor finish. I don't know where the fire lines and where your ducts and everything goes and what's the floor to floor height you get. And at that, the apartments in this complex were going for $1 million, right? So we don't understand a lot of things. So anyway, just to continue with what Dr. Julie is saying, developers want to construct buildings at minimal cost. University courses and building codes use the word system for 2D components such as flat slabs, and 3 building codes not recognizing salty air above ground for concrete cover requirements. Question: in India, how are or will such things be addressed?
Yeah, let me say this upfront. The revision of the concrete code is happening after 43 years. If it had happened after every 3 years, 4 years, we could have made these changes 2, 3 at a time. And by now we would have made 30, 40 major changes. But if you do it after 43 years, we will have to make monumental changes. And that is what we are up against. And I hope that at least after this revision, we will do it more often, which only means that more people should participate in the development of standards and give their time for the development of standards.
So at the risk of saying something which may embarrass Professor Murty, I'm still going to do it. I think we are very lucky right now in India that we are very lucky to have had Professor Murty agreed to be part of this webinar, and I think everybody has had some idea of the depth of his knowledge and understanding. He started out with he has a PhD from Caltech, and he has been the director of an IIT and so on. So I don't want to get into that. But the point I'm trying to make is we are very fortunate in India right now that Professor Murty is the chairman of the Earthquake Code Committee. So all the earthquake codes, and I don't know how many there are, how many codes are we planning? I mean, right now we have very few codes.
Right now we have about 10, 12.
Yeah.
But time ahead, we will have many more. Yeah.
We'll have, I think right now there's a plan of
the pipeline this year itself.
Yeah, so there is a plan of having more than 20 codes. So all of that is being done under him. And also very importantly, one of the reasons why this webinar has been done is also it gives us an occasion to research, to study. And a lot of this goes into the mother concrete code, which is the IS 456, which I would say, your ACI 318 is actually, an agglomeration, a collection of a lot of our codes. But for us, the mother concrete code is IS 456. And I'm happy to say that even that IS 456 code, Professor Murty is the primary driver for that code, and I think we're all expecting to to have very, very sweeping changes coming in it. And one thing is that every time a new code comes in, and Professor Murty has had a very big hand in it, everybody's complaining. The whole industry complains because they think he is too harsh, right? Because he's too strict. But then, when events happen, I think the wisdom it kind of dawns on people. And of course, somewhere we come to a point where we have a sort of balance. So I think that's the way we are going, and I think it's very good at this point of time that we are also having structural engineers who are participating in code writing, and they're going beyond professional practice or the business of running a structural engineering practice. And I think even getting young people like Hemal is something which we're very happy to have had for the first time.
Can I add for the first two parts of the question, developers want to construct minimal cost. This is universal.
It's universal.
All I'm saying is there's a sequence: safety, functionality, service, durability or sustainability, and then economics and aesthetics. The first three are non-compromise situations: safety, functionality, and sustainability, in that order. And then the issue is about aesthetics and economy. I think the game is that if everybody is concentrating only on economy and putting that on the top, and safety is somewhere lost in between, the dignity of the profession is getting eroded. I personally would like to bring safety, functionality, and sustainability as top three, and only negotiate between aesthetics and economy, right? Coming to the second question, it is unfortunate. I agree with you. It's unfortunate that we use the word system. And that is why this time in this presentation, we are very careful. When Professor Goswami was making his presentation, he told us that he will want to use flat slab as an element, and that the rest of it is a system, but this is only an element. And I also changed my slide one word. I said it's an element and not I closed with that at the end. And we are learning this. I think it is important to share this, humility to all others, so that we don't perpetrate the negatives too far.
Right. Okay, so Hemal Modi is saying failures are an opportunity to learn and build stronger structures. The current codes can adopt many structural integrity related design from practices from ASCA, ASCI. Dr. Murty mentioned that she take into consideration the use of stringent requirements rather than shying away from designing them with a complete ban. Do we plan to have a detailed commentary? Yes, so this question, keeps coming all the time, that can we please have a commentary. So I think that's something which I think the code committee is acutely aware of, right? And,
yes.
And there is some activity.
456, we are trying to write the commentary for alongside the provisions and not later. And so we hope that we can release both of them as a draft for people to look at and then comment on. Because we could be wrong in some items because of our interpretation, but the country cannot be wrong as total wisdom. And so we will share that draft commentary and draft clauses also with you. Okay. For IS 456.
Okay, so then there's one question by Mr. Dulal Koldar: post-tensioning of flat slab is permissible or not? Yeah, but we are not talking this time of post-tensioning, but your answer, the short answer is it is not verbatim. It's not verbatim, and it is allowed, but there are lots of ifs and buts, and let's hope that we can have a more detailed discussion. And I think there are people here who would like to be participating in it. Then there is was the failure due to progressive collapse? Okay, I'm going to leave that. There is a general lack of awareness, appreciation towards the serviceability issues, long-term deflections, crack, this, with very thin slabs being increasingly provided in flat slabs, that with PT coming in, reducing the slab thickness even further. Buildings these days, the serviceability issues are becoming even more worrisome. Okay, that was a comment, not a question. What is your opinion on suitability of using flat plate system in zone 3 areas? Anybody wants to take that? Okay, there's one question again, which is come, building is survived for 40 years. So I want to give that with a completely non-technical analogy. I have diabetes, I have high cholesterol, I have thyroid, I have hypertension, I have all of that, and I'm living. Is that proof of, well, I don't have all that, but I'm just giving an example. Is that proof that I'm healthy? No. I mean, I can die any moment. It just means if I've survived for 40 years, it just means I'm very lucky. It doesn't mean I'm healthy. Okay, so I would use the same analogy to say that, just because a building has survived for 40 years doesn't mean that it is safe. Let's not conflate the survival of a building with the safety of a building. And I think that's something which all of us need to understand. And I think that's another thing. After an earthquake, we always tell people that just because your building survived this earthquake, do not be under the illusion that your building is going to be safe for the next earthquake of the same magnitude, of the same ground motion, and so on. So the short answer is that, building survived for 40 years doesn't tell me anything, right? It just doesn't tell me. All it's telling me is that it was just waiting for the as Professor Murty will say, for two pounds of apples, 2 pounds of extra apples, which would be the tilt point. And in this case, the tilt point could have been, as Hemal was saying and other people were saying, is excessive corrosion. So but the point is that if there is a marginal design, it may survive for a few years, but at some point it can catch up. And at some point it won't catch up also, right? I mean, so it's, I think luck has a large part to play in all of this, but if you don't want luck to be participating in whether your building survives or not, just build it right, and not marginal designs. What are your views about post-engine? No post-engine questions. Maybe know the latest status of 456 2000. Not this time. Okay, I do all buildings need to be checked for latest provisions and give stability certificate regularly? So this is an important question. I think we need to respond to it. The question being asked by Satish Kumar is, do all buildings need to be checked for latest provisions and give stability certificate regularly so that these types of disasters do not happen? I think, if I may, because I'm a practicing engineer, let me just give it a shot. And I'm sure Professor Murty and Professor Goswami will have a completely 180 degrees opposite response from mine. So let me take the first shot. Mr. Satish Kumar, I think it would be very foolhardy for us to give stability certificates. Okay, wait, let me rephrase it. I think that nobody pays you to give a stability certificate for reanalyzing the entire building as per today's codes, right? You cannot. When you are giving a stability certificate for an existing building, you have to clearly state unambiguously that the building is safe and stable for the loads it was intended for at the time of its construction. That is what you need to say. Because if you are going to say it is safe and stable as per present codes, most likely it's not going to be, right? And the question is, do you need to retrofit all your buildings to satisfy the current codes? No. The codes are very clear that you need to satisfy the current codes only if you're going to have very significant interventions in your building, right? Okay. I think we've come to the I think, okay, let me just see how many more questions, because I think this is like endless. Benjamin Moore says India and US compete for materials. This is India's great advantage of labor cost. It would therefore interest me to know what extent the panel feels that any shortcuts taken in Florida or elsewhere are predominantly a matter of deficient materials versus deficient labor. That's an interesting question, but, I want, Mr. Benjamin, I think, we are treading on a little bit of a shaky ground when we try to talk a little bit, and comment too much about a way of construction which we are not so familiar with. I mean, I think all of us, Professor Murty, myself, has spent time in the US of A, at least 4 or 5 years, but that has been quite a while ago. And I think it's also not our place to be commenting on whether it was deficient labor versus deficient materials. Professor Murty, do you have another?
No, I think it's, see, I would say that the matter is sub judice and there is a competent group of people who are looking at that subject.
Yes, exactly.
We have stolen this opportunity today to discuss the Indian scenario of a possible, use of a similar system in India.
Okay, great. So I think that we've reached 7:30, and I think it's a perfect time to thank everybody. And I'm going to ask, I think IIT Madras server seems to have frozen because both of them are not able to see, I think they're frozen. So may I ask Sanjeev to do the honors? Let me just introduce Sanjeev. Sanjeev is the brain and the brawn behind Structural Engineering Forum of India. I don't think we would be able to run it if he was not there. He is a structural, well, he is a civil engineer by education from IIT Kanpur, and he does a stellar job in running Structural Engineering Forum of India. Thank you very much, Sanjeev, for a wonderful effort and pulling this through. And I'd like you to do the honors to close this.
Thank you very much, audiences, for your patience and active participation into a very important structural safety issue. And we look forward to active engagement from our guiding pillars of structural engineering in the country, like Professor Murty, Ms. Alpa Sheth, Professor Rupen Goswami, who have been actively engaged into code drafting and code committees. Looking forward to see you again in this forum, and thank you very much again. With this, we may stop this webinar.
Thank you very much.
Yeah.